Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to tell you about a very, very important algebraic condition called the ascending chain condition, which crops up in many, many parts of algebra. Where I want to show you how it comes into play is to show that the argument that you have for the existence of prime factorizations in the arithmetic of integers can be extended to the existence of prime factorizations in Dedekind domains. So this is something that's very important in algebraic number theory, and perhaps in many ways this is where the condition comes from. Okay, so let's just go to this factorization argument, and then we'll see where this condition arises. Okay, suppose you have now here R is some Dedekind domain. Okay, so remember what that is. So that's just some commutative domain, and we're going to insist that every ideal is actually an invertible ideal. Okay, so that means that if you have a containment of ideals, actually you can factorize the smaller ideal as a product of the bigger one and another ideal. Okay, so that's the importance of that. Okay, so that gives you an environment where the factorization works fairly similarly to what you see with arithmetic. Okay, so containment really gives you factorization. So let's suppose you're given an ideal here, I inside R, okay, and we're going to just try to find the usual argument for trying to show that there exists a prime factorization for integers and see whether we can do it on the ideal level. Okay, so suppose you have an I here, and maybe it's prime. If it's prime, then you can stop, or maybe this is the R, okay, so if it's R, then of course you can stop as well. Suppose this is I, then if it's not prime, then you can write it as a product of ideals, such, or you can rather find a product of ideals, both strictly containing I, but the product is contained inside there. Okay, so since you have some ideal that's bigger than this one, okay, so that means that actually you can factorize it. Okay, so that's something that we saw with Dedekind domains. So suppose now you can factorize this. Now, if both of these are prime, you can just stop. Okay, but what happens if you don't have that situation? Well, maybe neither of them are prime. If neither of them prime, then you can do the same thing. You can factorize them into even bigger ideals. So suppose that I0 is now equal to I00 times I01, and that I1 is the product of I10 times I11. Okay, so maybe that some of these are prime. Okay, so you can stop. But the ones which aren't prime, you keep factorizing again, and you'll get an even bigger ideal. So maybe this I00 you can further factorize into I000, I001. And you keep going, okay? So the point is that before, when you do this with integers, each time you factorize, okay, you get something smaller and smaller. Here what's happening is the ideals get bigger and bigger. So what you want to do is, and what we see from this argument here, which we just repeat the usual factorization or existence of factorization argument for integers, okay, is that if you can't factorize this I into primes in this Dedekind domain, then what happens is that by re-indexing these, and so swapping the order of these if necessary, what you can find is there's a chain of ideals, an infinite chain of ideals, starting from I, and you get something bigger, I0, maybe, and then something bigger still, I00, and then I000, and so forth. You get this infinite increasing chain, strictly increasing chain of ideals. Okay, so what we want to do is to say basically this doesn't happen. And when this doesn't happen, then we say that the ascending chain condition holds. Okay, so let me state it more precisely here, and we'll put it in the more general setting. Okay, so suppose you have some ring R. Okay, as usual, this will be unital, but it doesn't even have to be commutative. Okay, and we have a module over that. Okay, we say it satisfies the ascending chain condition, and even in the literature, this is usually abbreviated to ACC. If the following holds, you look at every possible chain of submodules, M0, M1, so forth, and here you don't have inequality. Let's suppose that they're potentially equal. Okay. Okay, so let's just, you have some chain of submodules like this. Then this stabilizes in the sense that eventually, from some point on, say n, you'll have mn equals mn plus 1 equals mn plus 2, and so forth. So you don't have this strictly increasing chain of modules like you see with a strictly increasing chain of ideals here. Okay. So another terminology for this is that we say also that this module M is noetherian. And this is after Emmy Noether, who introduced this condition, and she was inspired by the number theorists like Dedekind before her. Okay, so what about the ring itself? We can also talk about the ring satisfying this ascending chain condition, or rather being noetherian. It's a little bit more subtle because we have a non-commutative ring here. Okay, we say R is left noetherian. Okay, if the left R module R itself is a noetherian module, and we'll say it's not right noetherian if the right R module R is noetherian, and we'll say it's noetherian if it's both left noetherian and it's right noetherian. Okay, so let's just do a little simple example of something which is noetherian, which also shows you how it captures what's going on in this argument here. Okay, so this argument was for showing that in the integers z, okay, there exists prime factorisation, and that's because when you keep factorising, eventually the numbers get so small that eventually you have to stop at primes. Okay, what's happening in this case here is, well, let's have a look at all the chains of ideals inside here, and let's just look at a simple example, and then you see why it's noetherian. If you start with 12 like this, okay, that's some ideal that may start your chain. Okay, when you get something bigger, okay, then what you'll need, since it's a principal ideal domain, you'll need a factor of 12, so you'll get something like, I don't know, maybe 6, okay? And then to get something strictly bigger than that, you'll have to get something like maybe another factor of 6, so maybe 3. And you can see you're getting some smaller factors here, okay, that corresponds to the ideals getting bigger, and eventually you have to stop, okay? And that's because, of course, the magnitude of these numbers here is getting smaller and smaller, and it can't go indefinitely, okay, because you start at 12, you can't go indefinitely down towards 0. Okay, so that means that Z itself is noetherian. So that's the first example. Okay, so let's go to some basic properties of this concept of being noetherian, okay, and noetherian modules. So we're going to work here over R is any ring here, and we're going to let R be some left R module, okay. So you should think of this condition here, the module being noetherian, as a type of finiteness condition. And I'll make this fairly precise here, okay. It's saying something about how big the module is, okay. So the first thing is that to check something is noetherian, okay, suppose it has a submodule n. To check that this is noetherian, you can check that both n and m mod n are noetherian. Okay, so in particular, if m is the direct sum of two things, okay, if it's direct sum of two things, so one of them may be a submodule, and the quotient by that submodule will be the other thing. So in other words, if it's a direct sum of two noetherian modules, then it's noetherian. And also, if you have a direct sum is noetherian, then each of the components is noetherian, okay? But this is more general, okay? It's saying if you have a submodule, to check whether m is noetherian, you just have to check the two component parts, so to speak, of it are both n and m mod n, okay? If you can find such a submodule, okay? So that's a rather nice result, okay? And it allows us to do a lot of induction to show that things are noetherian, okay? So the way you should kind of think of this is that if this module M is finitely built out in this way, it's got this finiteness condition, if and only if the submodule and the corresponding quotient have this finiteness condition. Okay. The second result here really shows you why this is important, other than just for using this factorisation argument. Okay. So M is noetherian if and only if every submodule is finitely generated, and that includes itself. So it's actually a stronger condition than itself being finitely generated. Okay, it's stronger than it's being finitely generated. And it also shows that why this is such an important condition, because suppose you're playing around with a noetherian module, okay, then it doesn't matter what submodule you look at it, you're always staying in that finitely generated sort of environment. So if you want to be in a situation where you're working with things, okay, and you're playing around with them, and you want to make sure that, oh, you're always finitely generated, then the noetherian condition is often what you want, okay, because it means that even if you look at a submodule, okay, it's going to stay finitely generated, okay. And then, of course, the quotient of a finitely generated module is finitely generated, but you can look at a submodule of a quotient, and that's going to be finitely generated, okay. So that's a very good condition that you can impose to guarantee that if you're not, doing things like forming infinite direct sums of things and that, you can try to stay inside a finitely generated setting. Okay, so I don't want to go through the whole proof of this, but I want to give you some of the arguments because they're rather nice and they really show you a lot of interesting algebra and how you can work algebraically. Okay, so this is very, very typical sort of an algebraic argument. Okay, and this condition also it gave rise to a lot of algebra. Okay, so let's just see what happens here. So suppose now we have some infinite chain of submodules. Okay. And we need to assume that it's strictly increasing, or just assume that it's like that. Okay. We want to show that it stabilizes. From some point on, all these modules stay the same. Okay, they stop increasing. Okay, and we'll do it in the direction where we're going to assume that this both n and m mod n are noetherian, so they satisfy the ascending chain condition, and we want to show that m satisfies it, so we want to show this stabilizes. Okay, that's what we want to do. We'll just do this direction. Okay, the forward direction is easier, and it's a similar sort of argument anyway. Okay, so we know that n is noetherian, so how can we use that? Okay, the ascending chain condition there. Well, to get a chain of submodules of n, what you can do is you can take this and you just intersect it with n. Okay, that will be submodules of n. So since you have the ascending chain condition of n, that means that for r large enough, okay, when you look at this chain where you intersect this with n, so you'll get things like mr intersect n, mr plus 1 intersect n, and so forth. If you make r large enough, you can assume that this stabilizes, so they're all the same. Okay, so the intersections of this chain with n stabilize at some point. The other thing to get a chain of submodules, which is inside m mod n, is you can take the image of this inside the quotient m mod n. And if you know your isomorphism theorems well enough, then you'll see that the image is going to be something like of mr will be mr plus n over n. Okay, and since m over n is noetherian, okay, it means that from some r large enough, okay, so you can make it large enough so this holds, and also this condition holds. Okay, so you the images of this chain from mr onwards, okay, inside m mod n stabilize. Okay, and I want to say that if both of these stabilize at r, then actually the original chain of submodules stabilizes from that point on. So mr equals mr plus 1 and so forth. Okay, and the argument is rather nice and is typical in algebra. Okay, so what we'll do is we'll first show that since this is contained inside here, we'll show every element in here, say mr plus 1, is also inside mr. Okay, so let's do this. So the first thing is, of course, you have to use these two conditions. So we use the first one here, okay, which says that mr plus n equals mr plus 1 plus n. So little mr plus 1 is inside here, okay. We'll give you something inside here, mr plus 1 plus n, which is equal to this. So you can write this out as a little mr, okay, which is inside big mr, plus some element of n, little n. Okay, so that's the first thing. That's using the star. We're going to use the dagger next, okay, to try to get more information about this. Remember, we want to say something that basically says that this is inside mr. Okay, that's what we want. So let's have a look at n, which is just the difference of these. So n equals mr plus 1 minus mr, and see where that is. So the first thing is that, well, we knew that n was inside big N, so that's something we know. Also, mr plus 1 is in this big mr plus 1, and little mr is inside this big mr. So since this is also inside mr plus 1, this is the difference of two things in the module big mr plus 1. So this is also inside big mr plus 1. So it's in the intersection of n with big mr plus 1. And now we use dagger, the fact that this chain stabilizes when we're in n. So if you're inside here, you're also inside here. So this is actually inside big mr intersect n, and in particular inside mr. So what does that tell you about this little mr plus 1? Okay, which is your arbitrary element of big mr plus 1. Well, it was the sum of these two. Well, this is of course inside mr, but this n we also said was inside this intersection, and in particular inside mr. So that means that the sum of them is also inside mr, and that gives you the equality here. And you can apply this argument, of course, to show that mr plus 1 equals mr plus 2 and so forth. Okay, so that gives you the fact that, yeah, in this case here, if n and m mod n are noetherian, then so is m. And it's quite easy using a similar argument to show the forward direction as well. What I want to show you now is part B, or at least one half of it. Okay, So I want to show you, let's do which part? Let's do the forward implication, okay? And we'll do it via the contrapositive. Let's suppose that there's an infinitely generated submodule of here. Then we'll show that it's not in the theorem by showing that there is some strictly increasing sequence of submodules, okay? So let's suppose n is some submodule not finitely generated, it has infinite generators, or rather it's infinitely generated by n1, n2, n3, and so forth, and it really needs every single one of those generators, okay? You can't drop them, okay? Then what happens is that you can form the following sequence of submodules. Start with r times n1, okay, what's generated by n1, and then what's generated by n1 and n2, and since you need n2, this is going to be strictly bigger, okay? You can't drop that. And then this is not the whole of n, it's infinitely generated, so we can now find a third generator that's required and gives you something strictly bigger, Rn1 plus Rn2 plus Rn3, and you keep going. And that's how you get your strictly increasing chain of submodules. Okay? It's rather nice how these algebraic arguments work. Okay, so to go in the converse direction, you can actually reverse this quite nicely. So suppose you know now that every submodule is finitely generated, okay, then how can you show that these things stabilize, okay? So suppose you're given some sort of sequence like this, okay, then what you can do is you can look at the union of m0, m1, and all of those too, okay? And that's finitely generated. And since that's finitely generated, well, the finite generators have to live somewhere in some of these m's, okay? And so if you pick the one which contains all of them, okay, there's a finite number of them only. So from that point on, once you contain those finite number of generators, and they have to be somewhere in that list because you're just taking a union, okay, it will stabilize. Okay, so actually, it's quite easy to see both implications there. And that's rather nice. And it shows you why this noetherian condition is really, really important. Okay, and there's a lot of work going on studying, you know, if you want to study a nice class of rings, noetherian rings is a very, very nice class of rings to study. Okay, so let's now go back to the question of the existence of factorisations. So suppose now you have some Dedekind domain, R. So the first thing is that it is in fact noetherian, okay? And the second thing is that that means that any ideal can be prime factorized. Okay, so why is this noetherian? So remember, Dedekind domain means that every ideal is invertible, and we saw in the previous video in this playlist that invertible ideals are actually finitely generated. So actually every ideal is finitely generated. I should say that every non-zero ideal is invertible. That's what Dedekind domain means. But of course, the zero ideal is finitely generated. Okay, so this is actually noetherian, and then we can go back to the original argument that we use for the existence of prime factorization in integers. Okay, so this argument here to see that actually yes, okay, if you do this method of trying to prime factorize, okay, if this is not prime, so it's going to be not maximal, okay, then you can find a bigger one. And then you can keep finding a bigger one, strictly bigger one, okay? But of course, at some stage, this will have to terminate, and so you have your existence of prime factorization in this case. Let's now look at some important examples of noetherian rings. So the first simple example is the principal ideal domains. Any principal ideal domain is noetherian. And the reason for this is very simple. What you can do is you can look at any ideal inside here, and of course it's principal, so it's generated by one element, and in particular it's finitely generated. So any ideal inside principal ideal domain is finitely generated, and so that means that this the ring itself is noetherian. Okay, then next very important example is called Hilbert's basis theorem. Okay, and it says that if you have a noetherian ring R, then the polynomial ring in with coefficients in R in one variable is noetherian, and since this is noetherian, you can apply induction on this to say that the polynomial ring in any finite number of variables, okay, over this R is also noetherian. This was a really, really big theorem. It's a hard theorem, so I'm not going to prove it. Okay, it would probably take a video in itself to do the proof of this, although it's rather nice. But it really was a bit of a bombshell, this proof here, and it really kicked off this idea of using a lot of these algebraic, non-constructive arguments in pure mathematics. And it really was very useful when he was studying invariant theory, which is a big part of algebra at that time. Okay, so suppose R again here is left noetherian. Okay, in that case, then any quotient of this R, okay, any quotient ring is also left noetherian. And finally, sort of going on this theme B here, suppose you have some R is noetherian, and you have a commutative R algebra, which is finitely generated as an R algebra. Then suppose that A is such a finitely generated commutative R algebra, then so is A. Okay, so to be a finitely generated commutative R algebra, what does that mean? Okay, essentially that just means that you have this commutative R, and you have the finitely generators. So maybe there are n of them, so you just form the polynomial ring of in R with those n indeterminates, and this A has to be a quotient of that polynomial ring. So if you put these two parts together, you get part D. Okay, so as I said, I'm not going to prove part B for you, but what I'll do is I'll prove, since this is a corollary of this, I'll prove this one in a very special case where it's not just finitely generated, A is not just finitely generated as an R algebra, but it's finitely generated also as an R module. Okay, so let's look at that special case where A is finitely generated, say, by A1 up to AN as an R module. So you can write A equals RA1 plus all the way up to RAN. Okay, so what does that mean? So that means that, well, now I can form a surjection of left R modules from n copies of R, and direct sum n, to this RA. Okay, so what's that surjection? You just take this n tuple here, and you send it to the corresponding linear combination of this generators A1 up to AN. It's easy to check that this is a surjection. Okay, and this is a standard sort of technique when you want to express a module as a quotient of a free module. Okay, so that's what you have. You have this surjection. So in other words, as an R module, this R module A is a quotient, isomorphic to a quotient of this one here. So the first thing is that we're assuming here R is going to be noetherian. So so the direct sum of R with itself n times is also going to be noetherian. Okay, so remember, if you have a submodule and a quotient module which are both noetherian, then the original module, when you put them together, is going to be noetherian. And if you apply that result several times, you'll see that R direct sum n is noetherian, assuming that R is noetherian. And this A is isomorphic to quotient, so this also is noetherian. Okay, so you have this R noetherian R module. Okay, so now let's look at that, and let's try to prove that A itself is noetherian. So we're going to consider these chain of ideals, I0 inside I1, inside I2, and so forth, and we need to show that it stabilizes. And the key result is that you can think of this as not just a sequence of submodules over A, it's also a sequence of submodules over R, because R is contained inside A, so you can just restrict the scalar multiplication to R. So this is also a chain of R submodules, but remember, we know that as an R module, A is actually noetherian, so this chain actually has to stabilize. Okay, so using this rather interesting argument, you see that actually A is indeed noetherian. So this will be the actual situation that we'll use it when we want to look inside number theory at rings of integers. Okay, this is sufficient to show that the rings of integers are noetherian. Okay, and hence we can show later that they're actually Dedekind. Okay, so I want to just finish off this video with this little proposition, which is really, really nice, because a natural question is that one wants to play around with is, suppose you have some finitely generated module. Is it true that a submodule will also be finitely generated? Okay, so you'd like to work often in a finitely generated environment. And unfortunately, this is not true in general. But one instance where it is true, one environment where it is true, is suppose now that R is left noetherian. In that case, then M is an R module is noetherian if and only if it is finitely generated. So that tells you that in particular, if you have a finitely generated module, it's noetherian. And remember, every submodule of a noetherian module is noetherian. And since it's noetherian, it's also finitely generated. Okay, so in this environment here, okay, if you have a finite, if you're working over a left noetherian ring and you're playing around with the left modules, okay, if you have a finitely generated left R module where R is left noetherian, then every submodule is also finitely generated. Okay, and the proof of this is quite simple. Okay, so remember, M noetherian certainly implies it's finitely generated because every submodule is finitely generated. But for the converse, we're going to use an idea similar to what we'd have here. Okay, so what does it mean for M to be finitely generated? By this construction here, okay, that's equivalent to the fact that there's some surjection from R to the N onto M. Okay, So that means m is a quotient of r to the n. R is left noetherian, so this r to the n is also noetherian. And being a quotient, m is now noetherian. Okay, so if it's finitely generated, it implies it's noetherian as well. Okay, so that's why very often it's nice to work if you want to be in a situation where you're looking at finitely generated modules. It's good to work with a noetherian ring. I hope you enjoyed this adventure in pure mathematics.